And welcome back to the Electronics Experimenters Kit. Experiment 13, a microphone amplifier. This will be built on ideas we've got from experiments 10, 11 and 12. Just before I start the video, a quick shout out for this channel's sponsor, PCBWay. Your one-stop shop for all your PCB requirements, be it prototypes, assembly, flexi rigids, CNC machining, 3D printing. The instant quote is easy to use. Just put in the dimensions of your board, number of pieces, how many layers, thickness, etc. Upload your Gerbers, hit the quote now button and you're good to go. And delivery is very fast. PCBWay supplied the boards for the electronics kit, so back to the video. Right, back to the circuit. Here we can see the circuit that we built up on experiment 12, where we bootstrapped the output back to the input to provide us with some extra gain. Well, here we're doing the same, but we're coming at it from a slightly different direction, which removes the biasing from the input to Q1. So, without further ado, let's have a look at the new circuit. Well, looking at this circuit, you may ask, where did I start, or how did I start? Some of the values are not optimised for the best circuit design or best gain, but they're the ones in my kit, so I've used them. So, we'll be looking at very low level input signals. There will not be a great input voltage swing on the base of Q1, so we can bias it around its turn-on voltage, so we haven't really got to worry about where it sits. So first things first, let's pick a current to flow through Q2, R4 and R5. I'm going to stick with the 2 milliamp value that I've used in the other experiments. We want the voltage across R5 to be about the turn-on voltage of Q1. So as a starting point, let's pick about 0.6 volts. So using Ohm's law, we know that 0.6 volts divided by 2 milliamps equals 300 ohms. But we have a preferred value of 330 ohms in the kit, so I'll use that. The value of R1 was chosen to provide a reasonably high impedance to the gate of Q1 of the bias voltage being fed back from R5, and thus it's a high impedance as well to the input signal. Next, I want the voltage on the emitter of Q2 to be about mid-rail, e.g. half a supply rail of 9 volts, so we're aiming for about 4.5 volts. So again, 4.5 volts divided by 2 milliamps is about 2,250 ohms. We subtract the value of R4, 330 ohms, which leaves us with 1,920 ohms. But again, I use the preferred value of 1K8 because I got them in my kit. Q1's collector load of R2 and R3 were picked as 10K, as again I had 2 free in my kit of bits. But these should still give a reasonable gain without the bootstrapping. We'll test this later and then we'll check to see what it is when the bootstrap capacitor is put back into the circuit. Now the DC quiescent operating point is all based around the chosen current to flow through Q2. With Q1 off, the base of Q2 is pulled high by R2 and R3, and this turns it on, so the current starts to flow. And as the current builds up to the 2 milliamps, the voltage across R5 is starting to increase as well, and it will be building up to about the 0.6. As it gets to the voltage required for Q1 to start to conduct, two things happen. As Q1 turns on, its collector voltage starts to drop, and it will fall to the point where it starts to turn off Q2. But if Q2 turns off too much, the current flowing will decrease, and so will the bias on Q1. So it will settle with a wanted voltage of about 4.5 on the emitter of Q2, which is what we designed it for, which then means that the collector of Q1 will be about 0.6 of a volt, or VBE, of Q2 above the emitter voltage, so about 5.1 volts. So I hope this makes some sense and you've kind of understood why I've tried to describe it. But now we go back to the circuit, we'll build it up and we'll test the voltages and see how well they go. Well, I won't go on too much about it, but the circuit is a bit strange because it's the way it forms. R1, the 100k feedback from the biasing to the base. We have 2 and 3, the 10k's with a collector load. The emitter going down to 0 volts. We have the supply going to Q2. The capacitor on the output. We have the 1K8 here, then the bridge and the 330 ohm there. So it's close to the circuit, it just looks a bit strange because it's kind of scrunched in to make it all fit on. And so if we look at the voltage on the base, or going to the base, we have 0.671, so close to the 0.6 we were aiming at. If we look at the voltage on the emitter of Q2, we wanted 4.5, we got 4.31, and if we look at the voltage on the collector, we were expecting 5.1 and we've got 4.96. So it's reasonably happy, and as you can see on the scope, we have 2 millivolts per division on the input and yellow, and we have 500 millivolts per division on the output blue. And if we switch the meter to AC and we come in, this is without the bootstrap capacitor in, so plug that in there. We might have problems here because we've got 2 millivolts going in, so we're pretty close to the bottom end of this meter. So that's 2 millivolts going in, and on the output we have 339 millivolts. So I don't know if you need to calculate that out, but 0.39 divided by 0.002, we got a gain of 169.5. So not too shabby, but if we bring the gain in, the capacitor in, I'll need to use that wire now because I'm going to jump from the emitter of Q2 to the bootstrap capacitor that's up here, and we'll clip onto there. And as you've seen from the output on the scope, it jumped considerably. So now we've still got the 2 millivolts going in, but now we got 1.72 volts on the output. So 1.72 divided by 0.002. We've now got a gain of 860. So pretty good gain. But it's going to be a bit subjected to the fact that the temperature of this transistor, Q1, is going to affect the gain, because we haven't got an emitter resistor here. So we're relying on the intrinsic emitter resistor to decide the gain. So it's like the collector impedance divided by the intrinsic emitter resistance, and we know that one of the terms in calculating the intrinsic resistance is temperature. So it's quite subjected to temperature. So look, just putting my finger on there and you can see the gain is rapidly dropping. Take my finger off and it sort of shoots back up. If I blow it, it might change it a bit, but that's giving us a really healthy gain.
Just a little recap on the circuit operation.
What happens at power up? There is no voltage on Q1 base as there is no current flowing through R5. Q2 base is held as high as it's pulled up to the 9 volt supply by R2, R3 as Q1 is currently in the off state. Current starts flowing through Q2 R4 and R5 as Q2 is turning on. When there is enough current flowing through R5 to generate about 0.6 volts across it, this 0.6 volts is fed to the base of Q1 via R1 and Q1 starts to conduct. As current starts flowing through Q1, the voltage at its collector starts to drop. This now controls the current flowing through Q2 in order to maintain the required base voltage of Q1. The voltage at Q2 emitter is just the sum of the voltages across R4 and R5 and was calculated to be about 9 volt divided by 2, so about 4.5 volts. So we can see, with a little thinking, this circuit is not too hard to understand. Well, now you might ask, how do we turn this into a user-friendly microphone amplifier? As at the moment the circuit has very high gain and which is influenced by the temperature of Q1. Well, the quick and dirty answer is more feedback, but this time we're going to use negative feedback as this will lower the gain and increase the stability of the amplifier. So let's just add 2 more components and restrict the gain to a maximum of say 50. So cue the next circuit. Well, here's the 2 new components. The 50k feeding back from the output and the 1k on the input. And the same sort of components that you would use on a normal op-amp circuit as feedback. So when the pot is at its maximum, we have 1k on the input, 50k feedback. So that's gain of 50. And when we reduce the pot down to nothing, we will have full feedback and no real gain. So let's pop back to the circuit where I've added those 2 components and we'll have a quick check to see what the gain's like and did it meet what we calculated. Well, here we are with the circuit. The extra components have been added. Apologise for that one overhanging the board, but I didn't want to unplug it and move it all that way a couple of holes, so it's just dangling over the edge. There's the pot. It's a 50k pot. That's a 1k resistor, and currently we can see that we got 86 millivolts on the output, two millivolts on the input, so 86 divided by 2, 43. So we got a gain of 43. So that's close to the 50 that the feedback pot and the resistor should give us. And of course it means that we can set the gain to a lower value should we want. And the scope's not going to like this. It doesn't like these low levels. It's a, as you can see, it's not a very good scope. Change one thing and all sorts of strange things happen. So we can basically wind it down till we've virtually got no gain. No gain at all. And we can wind it up. Anyway, I hope you found that informative as usual, and if you want to see more, hit the subscribe button, click the like button and hit the notification icon, and I'll catch you on the next one.